Hello and welcome back to the Cracking FAANG YouTube channel. Today we're solving the daily Leetcode question 432, all big O of 1 data structure. Design a data structure to store a strings count with the ability to return the strings with minimum and maximum counts. I'm not going to read all of the methods we need to implement, but basically just to summarize, we can initialize the object, we can increment a strings count by either incrementing it by 1 or creating it in the data structure. Decrement does the opposite. Get the max key, return one of the keys with a maximal count, and get the min key, which obviously does the same thing, but for the minimum. And all of these should run in big O of 1 time complexity. So on the surface, this problem seems pretty straightforward, and probably you're thinking, okay, well, I need big O of 1 time complexity, so I should probably use a dictionary. But the problem with using a dictionary to map some string to its count is that we lose the ability to basically get one of the keys with the maximal count, because there's no way to efficiently know all of the variables with a certain count, right? And to do that, we would basically have to go through the entire dictionary to get all those keys, and that could potentially be a big O of n operation. So we need some way to have a kind of like reverse mapping that will also tell us the counts and all of the strings that are in there. And that's essentially what we want to do. We're going to design our data structure such that we store, we're going to call it, a new data structure. We'll just call it a node. And in this node, we're going to store a few things. We're going to store the frequency of that node. So basically the count associated with this node, and then all of the keys that have that count. So that way we know that, okay, this node, let's say it represents the frequency of, 3. So all values in this node will be of count 3. And then we have keys, which is going to be all the words, which show up 3 times in our kind of data structure. So I don't know, like word 1, word 2, word 3. And what we can do here, and then we can also store the previous values. So we'll do this as like a doubly linked list. So we'll do the previous and the next, so we can easily know what the next node is in terms of like 1 count down and 1 count up, right? So this would be pointing to the node whose frequency is 3, and this would be the node with frequency is 4. So this handles the case of actually storing all of the keys for a different frequency, but we still need to know how to actually find them. So we'll have a separate dictionary, which is going to map each word to the node that it currently exists in, right? So this node here is one of these nodes. And every time we need to increment a count, we'll basically find, this is going to be the string. We'll look up this string in the dictionary, get its node, then either increment it or decrement it. So we'll have to remove it from our keys, and then put it in either, well, if we're decrementing, we'll go down, and if we're incrementing, we'll go up. And that way we can basically just then add it to the keys of the next node, whether we go up or down, and then update our dictionary here to tell us where it's now positioned. And that way, for everything, we'll be able to do O of 1, because when we need to basically get the words with the highest count, we simply, since we have a doubly ended linked list, we can keep track of the tail, and obviously the tail will be the one with the highest count. So the tail, we can just have a pointer to the tail to easily find it. We just simply return the frequency. That's the, we just return one of the keys in the keys at the tail. If we want to find the nodes with the smallest frequency, then obviously we go for the head node. And then in the head node, again, we just return one of the keys randomly. And there you go. So basically that's the intuition. We're going to have a node which is doubly linked, so we're going to go for the previous and the next, and we're also going to have a mapping for each word to the node where it exists. And within each node we'll have the frequency, sorry it's getting a bit messy, the frequency, the keys of this node which have that frequency, and then the previous and the next node. So hopefully this drawing, I know it's a bit messy, but kind of gives you the basic intuition. Now let's actually go to the code editor and type this part up. Okay, let's now code this up. First thing we need to do is actually define our node structure, which we said we would use, because obviously these don't exist in the wild. So let's just say class node. And what we want to do here is we're going to do def init. We're going to initialize it, and basically the node is going to be rotating, or not rotating, based on the frequency. So we want to say that the self.frequency is going to be whatever frequency we want to work with. And obviously it's going to operate as a doubly linked list. So we have a previous node and a next node. So we're going to say self.prev, and in the beginning this is none. Same with self.next. In the beginning this is just none. And what we want to do is, remember, we want to store all of the keys which have frequency. So we need to store these, right? Self.keys. And we want this to be a set because we don't want any duplicate characters here. So that is the node itself. Now let's actually start defining the all-one data structure. And let's start with the init function. So remember that we want to store a few things. We want to store the head of our linked list, and we want to store the tail of our linked list. So we can easily access the value with the maximum count because that's going to be at the tail, and the one with the minimum count is going to be at the head. And obviously we want to have the mapping for each word in our structure to the node where it currently resides in, so one of these nodes. So what we need to do is we need to say self.head, and we're just going to create a dummy node here. And we're going to say self.tail is going to equal to a dummy node. And we want to link these two because remember it's a doubly linked list. So we're going to say self.head.next equals to self.tail. And we want to do the same thing. Self.tail.previous equals self.head. Okay, so now we've linked them. And the last thing we need to do is the character map. So we're going to do the character map. And this is going to equal to char map. It's going to equal to just an empty dictionary. Okay, so that is kind of the setup here. Now let's do some of the easier ones, which is the get min key. So what we want to do is we want to basically check, the first thing we need to do is actually see if there's anything in our data structure. And the way that we're going to do this is we're going to say that if head.next, self.head.next actually equals to self.tail. This is our base case, right? If self.head.next is actually the tail, like we set it here, that means we haven't seen any characters. So there's nothing to actually return. So we can simply just return an empty string. So otherwise, if we have some values in our thing, then we obviously want to return the value from the head, right? And notice that the head is just a dummy node to actually just keep track of it, that we're not actually going to be storing anything in the head. The head.next is actually the node which is going to have something in it. So what we can do is simply just return one of the values from the head, right? So we can just return and we can just pick one of the random ones. So since it's an iterator, we can just do next iter self.head.next. So this will get the node that represents the head and then just the keys. So this will return one of the values from here. Okay, so now what do we want to do? We want to also do the same thing but for the max key. And we're going to have the same logic. So we're going to say if self.tail.prev is actually equal to self.head. So if the previous one of the tail is the head, then we're still in this base case where we haven't actually put anything in the data structure. So that means that we don't have anything because these are just dummy nodes. They don't actually store values. It's always their next or their prev that will store values. So if this is the case, again, we just want to return the empty string. Otherwise, we want to just do the same thing we did here, and we're going to return next iter self.tail.prev.keys. And yeah, just again, this iter and this next is just to prevent us from having to check, okay, how many keys are in here? Which one do we return? This will just get one for us without having to do anything. It will just return a key from there. So, okay, that is the get max key and get min key, pretty straightforward. Now let's actually implement the increment function or the decrement function, as these are the more complicated ones. So the first thing we want to do is actually check whether or not we have this key in our structure, because if it doesn't exist, then we can't decrement it. So there's nothing to do here. So we're going to say if key not in self.charMap. What do we want to do? We just want to return because there's nothing for us to decrement. So otherwise, the node where this key exists will be at self.map of key. Self.charMap, sorry. And now we need to remove this key from the node's list of keys because obviously we're decrementing it, so it will no longer have this frequency. So if we go back, so now we need to say node.keys .remove, sorry, we need to remove the key, right? And the frequency that we're working with is going to equal to node.frequency. Now, if the frequency is 1, then obviously decrementing it would mean that we're basically just deleting it from the data structure because its count is 0. So we need to check that. So we're going to say if frequency equals to 1, then we want to just delete the key from our map because it no longer exists. So we're just going to say delete self.charMap of key. Otherwise, we need to decrement the count and we need to move the key around, right? So the previous node that we want to insert it into, sorry, prev node, is going to equal to what? It's going to equal to the node.prev, right? Now what we want to do is we need to check whether or not the previous node actually exists. It could be the case that it doesn't, right? So we're going to say that if the previous node actually equals to self.head, and remember self.head is just a dummy placeholder, it doesn't actually store anything. So if the previous is actually the head or the prev node.frequency, if the frequency of whatever is linked before it actually doesn't equal to the frequency -1, then that means that there is no node actually between the two. So for example, if we have a node whose value is 4 and the previous node is actually 2, that means that 3 doesn't exist yet in our data structure and we need to create it because we can't just put it into 2. So we have to create 3, and the reason 3 could have been deleted because maybe there were no nodes in it. So we need to actually create the value here. So what we're going to do is we're going to create a new node. So we're going to say new node equals to node, and this is going to be frequency -1. And then we need to add the new key. So we're going to add new node dot keys dot add the current key. And then we need to basically now set the previous and the next pointer. So we're going to say new node dot prev equals to let's see, the previous node, this one. So prev node, and then new node dot next is going to equal our current node, right? So we just set that equal to node. And then let's see, and now we need to update the previous node to no longer point to our current node. Sorry, this is getting complicated, but yeah, we have to do it. So the previous node, its next now needs to get updated to the new node because technically it comes between our current node and itself. So we need to set that equal to the new node. And then we need to set our current node's previous to this new node as well. Okay, wow, that was a lot of linked listing, but we are almost done, hopefully. So now we need to just update the position in our map. So self.charMap of the key needs to point to this new node, which we've just created. Okay, so that's if the node was the previous node was the head, or the previous node actually its frequency wasn't our frequency -1. Otherwise, we just need to go into the previous node and actually just add that key to its count. So we're going to say the previous node dot keys dot add our key, and then we just need to update our map again. So we're going to say that self.map charMap of key equals to the previous node. Okay, so now what we want to do is we want to keep our data structure clean. So if after getting rid of this key in our current node, if the node no longer exists, we want to clean it up. So that way we don't have problems in the future. So basically, if there's no values in its keys, then we're going to delete it. So we now need to actually delete the node. Where's my placeholder here? Oops, did I mess up my indentation? No, it's fine. Okay, so we need to actually check if not node.keys. We need to actually delete this node so it's not just floating around there with nothing inside of it. So we're going to call self.remove node, and we're going to pass in the node. And now let's actually implement this function because we're going to need it. So let's define another helper function. So we're going to say def remove node self node. And what are we going to do here? So we need to basically just delete the node from the linked list. So the previous node is going to equal to the current node.prev. The next node is going to equal to node.next. And then we also have so we basically just want to link the previous node to the next node and then vice versa. So we're going to say prev node.next is going to equal to the next. God, I hate this keyboard, I can't type. Next node, and then we're going to do the opposite. So we're going to say the next node.prev equals to the previous node. Cool, so that will actually remove the node from the linked list. All right, we are almost there, guys. I promise we just need to do the increment, which is going to be very similar to the decrement. Unfortunately, it is quite a lot of code again, but it's fine. It's basically the same idea here. So if our current key is in self.charMap, so if we have a count for it, what are we going to do? So we're going to say that then the current node equals to self.map, char map for the given key, and the frequency equals to node.frequency, and then we now need to actually remove the key from this node, right? Because we're going to have to move it to the next one. So we're going to say node.keys.remove our key. Okay, cool. So now we need to basically put it into the next node if it exists. If not, then we can actually create it. So the next node is going to equal to node.next. And similar to what we did with the decrement, we need to actually check whether or not the next node is the tail or whether the next node's frequency is actually one greater than our current frequency. If it's not, then we need to create the new node like we did last time. So we're going to say if next node equals to self.tail, or let's see, next node.frequency does not equal to frequency plus 1, then we need to actually create the node. So again, we're going to create the node. So, God, my fingers are so cold, I can't type this morning. Okay, so we're going to do node, oh, Jesus Christ, frequency plus 1. So that will create the node. Now we actually need to add this current key to the node's keys. So we're going to say new node.keys.add key. And now we need to basically do all of the linking. So we're going to say the new node, its previous value is going to equal to the current node. The new node, its next value is going to equal to whatever the old next node was. So next node. And then we need to now link the current node, its next, to the the new node. Now that we've created the new one, we need to create the current one's next to be it, and then we need to basically, I think, do the opposite. So the next node, next, wait, where do we create next node? All right, it's up there. Lol. No, hold on. New node.next equals, no, this should be next node. Yeah, God, yeah, this is such a horrible question. So confusing. Next node, is previous value should be the new node. I hope I didn't get that wrong. And then we also, I think now we just need to update the actual dictionary. So self.char map of key equals to new node. Okay, God, I hope I didn't get that wrong. Makes sense. I think we did the exact same thing. Yeah, okay. Whew, okay, so otherwise, if this condition didn't fire, then we need to just handle the case where we need to increment the value in the next node. So the next node dot keys dot add the current key, and then we need to update the char map as usual. So key equals to next node. Okay, cool. So now we have updated it, but remember we still need to actually delete the key if it doesn't exist, unfortunately. So, or sorry, if basically getting rid of this, oh no, hold on. Oh no, this is the case where the key doesn't exist in the dictionary. So we need to close this if statement. Oh, this all should be nested. Oh God. Okay, there we go. Let me just zoom out, make sure I have this correct. So if, okay, so this is all nested correctly, so that should go here. God, I really hate this question. Okay, we will struggle together. Okay, so if the key doesn't exist, then obviously we need to create it, and then do all the linking. Fun. So if the key doesn't exist when we increment it, so let's see, what do we want to do? So we want to get the head of the linked list. So obviously in the case that there are no elements in the, let's see. Yeah, if it's not in there, then we need to get the, let's see, 1 second. Okay, sorry guys, I did this problem a long time ago and I forgot actually what my code was, but now I remembered. So we are basically at the part where we're inserting a key, or we're incrementing a key, and it doesn't exist in the map. So we need to actually insert it by creating the node or incrementing whatever the first node is. So we need to actually get the very first node, because that should store everything with a count of 1. So remember that the head is just a dummy node, so the true first node should equal to self.head.next. But remember, like we did when we actually deleted a key, we can actually get rid of a key if it doesn't have any values in it. So we need to actually check whether or not this value is the right one. And what we're going to do is we're going to check whether the first node does it actually equal to the tail. If it does, then that means we don't have any actual characters in here. So we don't have anything in the, no words in our data structure, so we need to actually create a new node. So if the first node actually equals the tail, or the first node has a frequency actually greater than 1, then we know that what ended up happening was we actually deleted the node whose frequency is 1. So we need to create a new node. So we're going to say that new node equals to node, and its count is going to be 1, and new node dot keys dot add the key. Now we need to say that the previous node of this new node is obviously going to be the self.head, and the new node dot next is obviously going to be equal to whatever we stored in the first node here, first node. Okay, so that part is fine. Now we need to update the head. So we're going to say self.head.next is going to equal to our new node. And we need to do the reverse. So we're going to say new node dot prev. Oops, no, we already did. Yeah, we already did that actually. So we need to actually just update the first node, its previous. So we're going to say first node dot prev is going to equal to the new node, and then we just need to update the char map. So self.char map for our key equals to new node. Okay, Otherwise, what's going to happen here? We need to just update the key, right? So first node dot keys dot add. So if the first node is actually the legitimate first node, we just add the key, and then we say self dot map char map char map of the key, and we're going to say that this equals to the first node. Okay, I think that should be it. Let me just double check. I think that's it. Yeah, let's see. I think actually we need to, okay, so after we did the update here, we need to check that we remove the key actually. So if the current key, so remember when we increment from one, if we remove it from another one, we need to actually check, similar to what we did in the decrement. So we're going to say if not node dot keys, we actually need to remove this key and delete it from the linked list. So self dot remove key in the node. I think now that should be fine. Let's see, please remove key. Great. Oh fuck. Remove key. Aha, there we go. Remove node. Okay. Wrong answer. Okay, give me a second. I'm gonna go figure out what's wrong with this, fix it, and then yeah, I'll be right back. Realize the mistake here in the actual increment when we are creating a new node. The current nodes.next should be the new node, not the next node. Otherwise, we wouldn't have updated anything. So I think now if we run it, we should be okay. Oh God. And accepted. Wow, Jesus, that was so long and horrible. Yeah, I will definitely just post the code in the comments because I'm probably trying to follow this will be complicated. But anyway, just do the time and space complexity before we go. Obviously, the time is big O of 1 because that's the requirements for the problem. Space complexity, big O of n, where n is the number of words. So yeah, that's this one. This question is horrible, just horrible. It's not hard. It's just way too much code. I mean, 100 lines. It's too much. Anyway, hopefully you learned something. Hopefully you didn't get too frustrated. If you enjoyed the video, why not leave it a like and a comment, subscribe for more daily videos, and I will see you in the next one. Bye.